If you would please, you need a calculator and you need your equation sheet out. So, guys, before we start, because we are going to start chapter 15 today, I want to sort of recap with you all of what we did in chapter 14, because it may seem like we did a lot in chapter 14 to you right now, but by the time we get to the end of chapter 15, chapter 14 is going to be like a blip on the radar, okay? I've brought this up before, but did you all notice that every reaction throughout all of chapter 14 was something plus water?
Yeah.
Okay. Well, there is an acronym that I made up that we're going to use a lot. Everything in chapter 14 I call a WOMIX problem. Not a woman's problem. Okay? Okay? A WOMIX problem. All right? These letters stand for something. Every problem we did in chapter 14 was of this type. Meaning, water was a reactant. And anytime we set up an ice table, what kind of numbers were put into that ice table? Molarities. Okay? Molarity. I'm running out of room. And in every ice table that we did on that C of ICE, ice, that line, we were subtracting X, adding X. Okay, so why did I come up with this acronym? Because, not today, but probably by next class, all three of these factors are going to change. We're going to start to see reactions that do not involve water, that do not have molarities, and we're not adding and subtracting X. And that gets its own acronym. But we're going to start to use this word as an adjective, a noun, a verb. You're going to start to speak in ways that your friends are going to be like, what are they talking about? Because you'll be like, oh, just WOMIX it. You just have to WOMIX that problem. Just WOMIX it. Okay? You'll know what you're talking about. No one else will. It's like our own little secret language. Okay? So, one other thing that makes 14 and 15 different. Okay? There are quite a bit of similarities, a lot of the same processes, but something that is going to make them dramatically different is that in chapter 14, every problem that we did really only had one thing to deal with. One weak acid, one weak base, one salt. 15, we're going to start to see multiple things thrown into one beaker at the same time. And you're asked to calculate the pH. Okay? So, the first concept that comes up in this chapter is something called the common ion effect. And I'm going to start off with this example of HF. Acid, strong or weak? Weak? Okay. If I handed you a beaker of HF, which I would never do because that would be completely irresponsible, gave you some numbers, asked you to calculate a pH in general, not details, how would you calculate a pH of HF? You do an ice table, okay? Well, we're now in chapter 15. I'm not going to have just HF, okay? I'm going to put something else in that beaker, like that. What is this? Acid, base, salt? What is this? It's a salt. What do salts do when you put them in an aqueous environment? They ionize, they dissociate. Do you see an ion in common between this acid and the salt? Yeah, the fluorine. So here's the situation. I hand you a beaker of HF, okay? Then we put something else in it. We put this salt in it. That salt ionizes. What that is essentially going to do, you have this nice happy little equilibrium system. You add this salt, you're adding more of that product. Think about Le Chatelier's principle. Shift right, shift left. Adding more of this is going to do what to this reaction? Shift. Correct. It will shift it to the left. Now, don't answer immediately. I'm going to ask it twice because I really want you to think about it. If I measured the pH of a beaker with HF only, nothing else, it would be in the acidic range. It's an acid. If you add this salt, which is going to cause a shift in this direction, okay? Let's say the pH was, I'm going to make up a number. Let's say the pH was 2. Then I add this salt. Will the pH change? Will it drop below 2, go above 2, or remain unchanged? Let me ask it again. Don't answer immediately. If a beaker of HF has a pH of 2, then we add this salt, which causes a shift to the left, will the pH drop below 2, go above 2, or stay at 2? I hear all three answers. Well, let me give you a hint. What determines the pH of something? Concentration of H+. We're doing something that's causing a shift away from H+. There will be less H+ floating around in the beaker than there was before. So, is it becoming more acidic or less acidic? Less. So if the pH was 2, once I add this, the pH will start to climb. It will go closer to 7. Okay? It will become a little bit more basic than it was because of that shift. That's what the common ion effect is. You're changing, you're affecting the pH by adding something else. And this doesn't apply to just acids either. Okay? If I have a weak base and I add a salt like ammonium chloride, that's a salt, they have an ion in common. We'll see the exact same phenomenon. Let's say that I hand you a beaker of ammonia and the pH is 10. When we add this salt, will the pH drop below 10, go above 10, or stay the same? It'll go below 10. It will become less basic because there will be less of this floating around. Okay, now, these two situations have a name, ladies and gentlemen. They are called buffer systems. And the very first, probably simplest kind of question you're going to see on multiple choice will be, which of the following combinations represents a buffer system? Okay, well there are two types of buffer systems. The first type involves a weak acid. Let's go back to the example on the previous slide, like HF. And its conjugate base are present at the same time. Now let's just review for a second. Let's review this term right here. A conjugate base, remember, is what your acid turns into after it gives away its hydrogen. What is the conjugate base of that acid? F minus. If you have these two things floating around in the same container at the same time, that is a buffer system. Okay? Now, where does this come from? Usually it's coming from a salt. Like on the previous slide, we had sodium fluoride being added. Okay? If I had, this is an acidic buffer system. A basic buffer system would be like ammonia, a weak base, and its conjugate acid. Let's review this term. conjugate acid is what the base turns into after it accepts a hydrogen. What is ammonia's conjugate acid? NH4+. If those two things are present at the same time in the same container, that's a basic buffer system. Okay? This is probably the most important word on the slide. Weak. Let me show you something here. What if I had HCl and Cl minus in the same beaker? Is, yes or no, is Cl minus the conjugate base of that acid? Yes or no? Yes. But I'm telling you, this is not a buffer system. Why not? Because that's a strong acid. Buffer systems are made up of weak things. Okay? Now, the question that may be burning in your brain, who cares? What's a buffer system? What does it even do? Why are we even talking about it? I'm going to give you a very practical, real-world situation. I want you to think about your human bodily systems. Anywhere in your body that contains an aqueous environment, your blood, your spinal fluid, stomach contents, okay? Anywhere in your body that is an aqueous environment, buffer systems are there, and you should be very glad. And I'll tell you why. Let's go with blood. Blood is about 85% what? Water. So what do you think the pH of your blood is? 7. Very close to 7. Okay? Let's say that you're incredibly thirsty one afternoon and you very quickly drink an entire can of Coke, like in under 2 minutes. You're really thirsty. Okay? Well, guys, any soda is acidic. All right? Sometimes very acidic. If you have a beaker of pure water and you pour an acid into it, what's going to happen to the pH? It's going to fall. It's going to drop. Okay? Anything you ingest is ultimately going to end up in your bloodstream. Okay? So if you ingest something acidic like a Coke, and it's eventually going to end up in your bloodstream, the pH of your blood should drop. But it doesn't. Which is a good thing, because changing the pH of your bloodstream can kill you. And I don't mean by a lot. Okay? I don't know what the magic number is, but you know, if your pH, your blood pH is normally 7, maybe dropping it down to 6.7 is enough to kill you. But the point is, what are buffers doing? Ladies and gentlemen, the purpose of a buffer is to resist changes in pH. They resist changes in pH. They keep whatever pH is there very steady. Okay? So you be grateful, ladies and gentlemen, because if you didn't have buffers in your blood, drinking a Coke would kill you. So say thank you. Thank you, buffer systems. Come on. Thank you. Okay. Now, is there math involved? You bet. All right? And guys, we're going to just take baby steps in difficulty here. What we're going to look at here is very much like what we have been doing, with one tiny little change. All right? The first thing I want you to notice is that this first problem does not have just one thing to deal with. It's got 2. Calculate the pH of a solution containing a mixture of, this is called propanoic acid. Okay? Strong or weak? Weak. Okay? And we've got something else. What is this? Salt? Acid? Base? What is this? It's a salt. Do you see anything in common? Okay. That ion is in common between these things? Is this a buffer system, yes or no? Yes, it is. It's a weak acid, and its conjugate base is also present in the form of a salt. All right, fine. Well, we need to get in the habit, because it's going to become really important later, of listing out our major species. What major species is always with us? Water. Okay? H2O. How do I deal with this guy? Should I write him dissociated or not? Why not? Because it's a weak acid. Weak things, you keep them together. Okay? What about this? Should I split it up, yes or no? Why? It's a salt. Salts dissociate. So, write them separately. So, we've got 4 major species. Well, the reaction that we're going to write here is going to be very much like what we've been doing before. Guys, this is a Wommack's problem. All right? Which, even though you didn't know that term, you should know how to do. Okay? Take the acid, add it to water. Acids do what acids do. They give away that hydrogen. And we get this. So far, nothing new. Here's where things are going to change slightly from what we're used to. Okay? We have, up to this point, every time we've done a problem like this, we've had a number here. We don't care about water. 0, 0. These are not going to be zeros anymore. Okay? So how do you know there is a foolproof way to know on this initial line whether there should be a number or if it's going to be a 0? Listen to what I ask you. Is this compound right here, this acid, in our list of major species? Yes or no? Yes. So that means there was some initially present. What molarity is it? There it is, 0.1. We don't care about water. Was this ion in our initial species? Yes. So this is not going to be a 0. Where did it come from? This guy? 0.1. How about H3O plus? Not present, so that should be a 0. But from there, it's the same. What kind of K do I want to use? How'd you know that? Because what's being added to water? An acid. You don't need to graph this one. I'm going to do it for you because this is just an example. Solve for X. It was given to me in the problem. The Ka was. Okay? Not a coincidence that X comes out to equal the same number. Yeah, what's in the parentheses ends up basically canceling out. Okay? How would I solve for pH at this point? What do I do? Negative log of this number? How do you know that doing that is going to give you the pH? Okay, because X is the hydronium concentration. Okay, negative log of this guy, we get this number. What do you think I'm going to ask you? Okay, does it make sense? Well, guys, that question is getting harder and harder to answer. Okay? Because we don't have just a weak acid. It got a little more challenging when we had a salt at the end of chapter 14. Now we've got multiple things. Well, let's go back. Was this a buffer system, yes or no?
Yes.
It was. What kind of buffer system? A weak acid buffer system. An acidic buffer system. It had a weak acid and its conjugate base. It's acidic. Is it? Yes. We're good. Right? You do the second one. Go. Does it make sense? It sure does. It's a basic buffer system. Okay. Now I'm going to tell you something that's going to make all your wildest dreams come true.
This is not. You don't have to take the Everyone gets a 5 out of 10.
Okay. All the work that we did for this problem and the one above it, totally unnecessary. Why did I do this to you? Why did I make you do this? Practice, because I wanted you to see what the products are. I wanted you to see what the longhand way is to solve these problems. The short way is by simply plugging values into an equation, which is on your equation sheet. I'm evil, aren't I?
Did you know Australia is home to all the top 10?
You know, I did. I did. Ladies and gentlemen, there is an equation on your equation sheet called the Henderson-Hasselbach equation. Right? Let me show you where it is. In this equation section, it is the second to last one, right there. Okay? Where it says pH equals pKa, blah, 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 blah. Okay? Now, listen. This is how it's written on your equation sheet. I rewrote this equation a little bit differently because I wanted to make sure you understand what is being represented in these brackets. Okay? First of all, this equation, which takes 10 years to say, I am from now on going to abbreviate it by calling it the Hendy-Haas equation. Okay? So from now on, anytime I refer to this equation, it's the Hendy-Haas. Do you see how ridiculous you're going to sound now? You're going to be like, oh, you just Womex it and then do the Hendy-Haas. Huh? Okay, anyway. All right. Make a big point in your notes. There is only one occasion that using this equation is appropriate. You may only use this equation if you are dealing with a buffer system. which you will be a lot. So you're going to be using this equation a lot. But we couldn't use it anywhere in chapter 14 because we didn't have buffer systems then. Okay? Let me help you get your bearings here because you may not know what, for example, pKa, you may not know what that is. Tell me this. How do you go from H plus concentration to a pH? What do you do? Negative log of this number. Okay. That is the exact same relationship to go from a Ka to a pKa. The negative log of Ka is called the pKa, which is what would get plugged in right here. Okay, now this second part, plus log of A minus over HA. Brackets, of course, mean molarity, right? I rewrote it like this because to me this is a little bit easier to understand, okay? We can use this with a buffer only. Well, tell me this, guys. Let's say I have an acidic buffer system, which means I have a weak acid, and what else must be present?
Salt.
A salt containing what? Its conjugate base. Weak acid, conjugate base. Acid, base. Even though it's a conjugate base, it's still a base. That means you're going to plug in the molarities for these two things. What if I had a basic buffer system? That means I have a weak, we don't flip it, it stays exactly the same. I have a weak base, and what else must be present? Conjugate acid. Molarity of the base, molarity of the conjugate acid. Let me show you an example at what a time saver this equation is. Okay? Calculate the pH of the following. 0.75 molar lactic acid. Ladies and gentlemen, this is what makes your muscles sore after you work out. Strong or weak? Weak. I've also got sodium lactate. Acid, base, salt. What is this? A salt containing what? The conjugate base of this acid. Is it a buffer?
Yes.
You got it. Which means we can use Hendy-Haas. pH equals. How do you get a pKa? What do you do?
Negative log of
Very good. Negative log of the Ka, which is given to me in the problem. Plus the log of base over acid. Be very careful when you answer this question that I'm going to ask you. I'm not asking you for a number. What is the base in this situation? Be careful how you answer. Lactate. Not sodium lactate. This is a salt. The base is just this ion. Now, it's a conjugate base, but it's a base nonetheless. What is its molarity? 0.25. Base over acid. What's the acid in the situation? Lactic acid. There's its molarity. Put this in your calculator and solve. Tell me what you get. Shout it out. 3.38. Is that a pH that makes sense? Yeah, it's an acidic buffer system. It should make sense. It should be in the acidic range. Now, I'm not going to ask you to do any math on this slide. I just want to show you something. Okay? I want you to look at this compound. That looks pretty yucky. This is actually an acid you are very familiar with. Acetic acid. It doesn't look like it, but it is. This is acetic acid. What about this, as bizarre as this looks? Sodium acetate. Don't ask me why, for whatever reason, when acetate is your anion, sometimes they put the metal at the end. I have no idea why. I don't know. It's like one of these little weird oddities of chemistry. Okay? Is this a buffer? You got a 50-50 shot. It's a weak acid and a salt containing its conjugate base. Okay, if I asked you, which I'm not, but if I asked you to calculate the pH, how would you do it?
The Hasselbalch.
Fine, good. Hendy-Hass.
Hasselbalch.
You can call it the Hasselhoff if you want. This is the pH you would get if you plugged everything in. Now, to me, guys, again, I know I'm just speaking for myself, but just calculating pHs of buffer systems, that's boring. Okay, who cares? What's the purpose of a buffer system? Make sure the pH stays the same. Okay, great. Let's test it. A buffer is no good unless you see what it's made of. So we're going to test it. I am going to add to this happy little buffer system this. What is this? Acid, base, salt? What is it? It's a base. What kind of base? Strong base. Now, just use common sense here. If you add a strong base to something, shouldn't the pH go up, like, pretty significantly? Just say yes.
Okay.
Yes.
Yes, Miss G.
It should. Okay? However, if you're going to add it to a buffer system like this, look at the change. Wow!
Whoa.
Okay? This doesn't mean a lot to you now, but I want you to understand that adding a strong base and seeing that the pH only goes up by 0.02 units, that's huge. This buffer is doing an amazing job. Good buffer, good buffer. Okay? Now again, are buffers all powerful? No. If you go back into the stockroom and start popping pellets of NaOH, okay, your buffers are not going to be able to handle that. We are not going to do this kind of math yet. Okay? We will, but not today. So what are we going to do? We are going to end, this is our final topic. Okay? Guys, the math is not the hard part. Okay? What I'm going to present to you on the next two slides, the last two slides of today, is probably the most important thing in this entire chapter. Because if you can't do what's on this slide and the next slide, you're toast. Okay? What I'm going to show you, there's no math involved on the next two slides. That's not the hard part. The hard part is when you get a problem where you've got not one compound, not two, but 3, 4, multiple things all thrown together. The hard part is, what is the one reaction that will occur? That's the hard part. So here we go. Okay, so just like on the previous slide, we're going to start off with a buffer system, and then we're going to test this buffer system. We're going to pour strong acid into it. Please give me a weak acid of your choice. HF, how did I know you'd go with that one? Could you please give me a salt that completes this and turns it into a buffer system? Okay, NaF, original, real original. Okay? Please give me a strong acid of your choice. HCl's boring. All right, HI. Hi. Okay. All right. So I've got a buffer system and I'm pouring a strong acid into it. Well, first things first. This is not a list of my major species. So we need to come up with that list. What's always present? Okay, H2O. How do I deal with this guy? Leave him alone. Why? It's a weak acid. Weak acids stay together. I know, what a weakling. What about this guy? Why split it up? Because it's a what? It's a salt. Okay. This guy. Why split him up? Very good. He can take it. Alright. We've got 6 major species, and I'm telling you that only 2 of them are going to react. And it's your job to figure out what 2 are going to react. Okay? Stop guessing. You have no idea what you're talking about yet. Okay? We are no longer in the land of Womex. I know you feel like you haven't really been there that long. You have, because you've been there all of chapter 14. We are now looking for neutralization reactions. What does that mean? Neutralization. What plus what? Acid plus base. Stop there. Stop there. Forget about the products. You learned in Chem 1, acid plus base yields salt plus water. Well, it doesn't always yield salt plus water. That was a Chem 1 thing. Neutralization means acid plus base. Stop there. Okay? We've got to find an acid in this list. Can you please tell me what are the candidates? What in this list is capable of donating a hydrogen? Okay, HF, what else? Water, what else? Okay? That's it. I have 3 candidates for acid. How do you know which one to pick? You pick the one that is the strongest. Any guesses? H plus. Let me tell you something. And you can quote me on this. H plus is the king daddy of acids. Okay? He beats out all other acids. There is no acid stronger than pure H plus. Okay? So he is my choice. All right. Now, acid plus base. What things in this list are capable of accepting a hydrogen? Na will not accept a hydrogen. Okay, F minus. I, H2O. That's it. Okay. Now this is not quite as straightforward. These are my 3 possible bases. Which one do you choose? The strongest one. It's not quite as easy as the other one was. You're right, none of them are King Daddy. If you're not sure, try some possibilities. Like, try I minus.
Wait, you just straight up try it?
Why is this not going to happen? It forms a strong acid, so what? They don't want to be together, they dissociate. This is not going to happen. So he's off the list. One of them is going to happen. Okay? I'm telling you, it's going to be this one. And I'll explain why. Okay? Let's say you're not sure. Here are my 2 options. What would this form over here? H3O plus. Okay? Hydronium. Hydronium. Okay? Not H plus. H3O plus. Both of these are acids. On the very first day that we started chapter 14, I showed you, or I told you that H3O plus is an acid. It's not strong, it's not weak either. It's right in between. So which of these is weaker? Which of these acids is a weaker acid? Okay, what does it mean to be a weak acid? They stay together. This compound wants to be together more than that one. I personally find it easier to think about what potential products would I get and how much do those products want to be there. Okay? That is the equation I would end up with. Let's do another example. I'm going to choose ammonia as my weak base. Can you please give me a salt that will turn this into a basic buffer system? NH4. Okay. Give me a different strong acid, not HI. Different one. HBr. We don't use that one very often. Okay? Tell me, please, my major species. Water. What else? NH3. NH4 plus. Okay? Okay? What are my acidic candidates? NH3 is not an acid. Three possible choices. Which one do you think I'm going to go with? H plus, King Daddy. All right. Let's think about our bases. What are the options? Okay, Cl minus, Br minus, H2O, and then H3. Why will it definitely not be these two? Because those would form strong acids. Not going to happen. Which one of these is more basic? Ammonia! Ammonia is a base. Water is very neutral. What is this going to form? NH4 plus. Okay. All right. Let's use a different weak acid, not HF. Let's do acetic acid, which I'm going to abbreviate HAC. Please give me a salt that will turn this into a weak acid buffer system.
Hey.
Okay. All right, fine. Fine. Okay, now we're going to test this buffer by adding a strong base. Give me one of your choice. We already used K. All right, let's go lithium. Yeah, good choice. Okay. Let's list out the major species. Go. All right, H2O. Okay. Okay. Acidic candidates, tell me. This is not capable of donating either. So I only have two choices. Which one of these is more acidic? Acetic acid, okay. Candidates for bases. What else? Any guesses? This is the king daddy of bases. OH minus. King daddy. The products, guys, are very logical. What do you think it's going to be? You got it. Okay. One final example. Let's go with a different strong base. Let's go really bizarre. Let's go rubidium hydroxide. Fine. Alright, we'll list out our major species. It's our final example. Can you tell me what the acid will be? Nope. Nope. NH3 is a base? NH4 plus. And the base? OH minus. Tell me the products. Water and? Good job. So, all right. If that made even a little bit of sense to you, you should be feeling pretty good about yourself. Okay?
I feel good about myself.
Because that's what makes this chapter challenging. Okay? Now, Marianne asked a great question. Is water just never going to be a reactant? No, it will. Okay? But guess what? If water was one of our reactants, do you know what kind of problem it is? It's a Womix, which you're used to doing and could do very easily. But the tricky part is knowing whether water, and there will be examples of this, when sometimes water is the strongest acid in the list, or water is the strongest base in the list. Okay? There are times when that's going to come up. Okay? So that's where I'm going to stop.